Hello everyone, my name is Volker Tresp. I'm with Siemens in research in Munich, and I'm also a professor at the Ludwig Maximilian University of Munich, where I teach machine learning. And yeah, thanks a lot for the organizers to giving me this opportunity to speak. It's a great honor, and I hope you enjoy the whole event and what I'm talking to you about. So we are all familiar more or less with the great successes of deep learning. So we have convolutional deep learning for analyzing of images, for recognizing faces. We have recurrent deep learning for analyzing sequential data, like in translation systems or speech recognition. Then we have reinforcement learning for optimization of games, and generative adversarial networks, which are quite recent, for these amazing image transformations, and then some technology bases embedding and presentation learning, and more recent attention and graph neural networks. But of course, deep learning and all other AI technologies need data. So it's sort of more or less understood why deep learning works so well. We have more labeled data these days, deeper models, new algorithms, end-to-end training. So you're really optimizing for the task we're trying to solve. Then the amazing computational power due to GPU, for example, and the community, which is extremely active, exchanges information. It's a very different story now to work with students than it was before, because now they're part of this community. They download code, they download papers, and there's a quick interaction of research and communication of research results. But there also we also need deep facts and knowledge. And for example, IBM Watson works on huge document repositories with rapid information extraction. In autonomous driving, you need detailed maps and GPS systems. In industry, we are talking about IoT, Internet of Things, and big data. In healthcare, you need patient data and patient profiles to make recommendations about treatments, for example. Then the web, and for humans, it's web content and something like Wikipedia. And I argue for machines, it's increasingly the knowledge graph. And it's not just a hype. So the world consists of things, entities, and constants. That's a pretty general fact. Then predicates specify the relationship between things. And if you have never seen a knowledge graph, here's one. So Albert Einstein is born in 1879. He's a physicist. A physicist is a researcher. Albert Einstein is in Ulm, born in Ulm. Ulm is a city. Ulm is in Germany. Germany is a state. And this, the advantage is that this is also very simple to understand for anybody. So the nodes are the entities in this knowledge graph. Persons, things, and so on. And a statement is an existing link. So this statement is that Albert Einstein is born in Ulm. And we have temporal knowledge graphs where we have a time index to the link. So a link might not always exist, only at some instances in time. So for example, a war between countries is happening at some times, but then hopefully they make peace, and then this link will disappear. So it's also a temporal and a beast. It's a temporal knowledge graph, and if the typical knowledge graph, although considers static information. And I argue it's very fundamental. It's very basic. It's not a hype. It's not an artifact which will disappear. It seems to be something a lot of fields converge to, and take this as a data representation or information representation or knowledge representation. And the basis for the knowledge graphs are deep facts. So primarily it's about facts. And the one breakthrough was the Google Knowledge Graph, which showed everybody that all the problems can be solved. It can be done. It can be made scalable. They made it maintainable because if the information is old, it's pretty much useless. And they showed that it can be useful for search, question answering, text understanding, and is embedded in many Google apps within the company, but also outside of the company in applications end users are using. In Siemens, we are also very active in the knowledge graph and other companies as well. And the reason, of course, is that it seems to be a stable technology and industry sort of discovered a lot of ways of how to use knowledge graphs. There's a tendency, one argument is that relational databases are everywhere in industry, and knowledge graphs are sort of opening up these databases and making them accessible and connecting them. So in industry, there's always the need to represent this type of structural data and also to work with it. But you can also apply it to social networks. So here's a person who went to a university, to a particular city. He plays soccer and so on. And then you can also attach unstructured data or web pages, text, videos, images. So you get a pretty complete information model of a user in this network. And this is what a company like Siemens is interested in. So knowledge graph has a lot of background information, and it helps you to find tenders and to analyze tenders, which might be interesting to you. It helps you in flexible manufacturing because it has well-documented facts about similar installations. It can be used in the supply chain by describing companies, what they are offering, to what price, how reliable they are, which quantities they can supply and manufacture. And then maintenance and repair, so you can analyze problems or text reports or reports of different kinds of problems which have occurred in the field, and then use that information to support and improve other installations. I would say, this is, I think, the right technology, plus minus, so there will probably be some changes, but basically I think it's a very stable and strong technology which will stay with us. But of course, it's also not doing miracles. It's not that all these problems are solved by themselves. A lot of these problems, like mapping ontologies and so on, are still very difficult problems. And we, in my team, we have looked very early on how to do machine learning with knowledge graphs. And in particular, we developed the RESCOM model, and it was published in 2011. It was the first embedding model for making inference in knowledge graphs. So first we translate the knowledge graph into a tensor. So a tuple has three indices: subject, predicate, object. So we map it to a tensor with three dimensions. So one for the subject, one for the object, one for the predicate. And we enter a 1 if at locations where this tuple is known to be true. So in this case, ijk is true, or ikj is true, and leave it 0 otherwise. Then we model this tensor by a factorization approach, and we obtain here a matrix, and each row stands for an entity in the knowledge graph, and this green bar here is a vector of numbers, and this is exactly the embedding vector or the representation vector for this entity. And we have the same matrix over here for the objects, and we pick the object we want to make a statement about, the subject we want to make a statement about, and then also figure out, take the right relational matrix here, so with one matrix for each predicate, and then by multiplying this vector with the matrix and the vector, we get a number out, and we can interpret this as a confidence that this particular tuple is true. So if we have a true tuple, so 1, which after reconstruction wants to become a 0, maybe it was a mistake in the knowledge graph, And the other way is more interesting. If a 0 wants to become a 1, it might be something we conclude to be true based on the patterns the algorithm discovers sort of in the reconstruction. And since then, this became an active research area. So this is our RESCOM model here for the experts. You might recognize some of the other approaches which are quite popular, and most recently the connection to deep neural networks in forms of graph neural networks, graph convolutional networks are also explored, and we are using in our world the ones in our team, the ones which seem to fit both for the application at hand. So for example, these convolutional networks work very well for single relation types. So there's only like a neighborhood relationship or node relationship. In multi-relational domains, often the RESCOM and this family of approaches works better. Okay, I discussed this already. This is a mathematical description of what is going on. Maybe we can skip it. This shows you why it is, or maybe more directly, why it's considered representation learning. So here we want to evaluate if Max likes Mary. So we map Max to his latent representation, Mary to her latent representation. Likes also has a latent representation here displayed also as a vector. And then we have some form of mapping. So if you use a tensor approach, it's a core tensor. If you can also put in a neural network here, and the output is the probability that this triple is true. And these latent representations are very important. They're entity specific, and they sort of represent properties, latent properties of these entities we're making statements about. Here's an application in industry. Using this triple reconstruction approach. Siemens offers a lot of components and in the automation area. So typically it's associated with the semantic family of products, and there are a couple thousand, so different configurations of these, so that adds up. So there's a lot of variety. And but we also have a reasonable amount of sessions per month, so 60,000 active users per month. So this is sort of maybe the closest thing Siemens comes to a social network business or social business here. And the goal was to improve the user experience with AI, essentially to produce something like a recommendation system. And here we're seeing the knowledge graph which was constructed. So an item is like a thing. In a movie setting, this would be a movie. In our setting, these are things you can buy or order. And solutions are sessions of a user. And if you only consider the blue and the white nodes, you would have a normal recommendation setting. But we're also providing background information on the items. So this item belongs to this family, S7-1500. It's a type controller, or this one has voltage 24, and it's a plug. And it turns out by integrating this additional information, the recommendations became much more meaningful. So here's some numbers, and there are different problems. One is, can we make a good recommendation for the entities we already know about and the users we already know about? But even then, we have an online learning problem, because we need to integrate very quickly a new information, new selection by a user or in a session. And there this our RESCOM approach is quite suitable, because it's a multilinear model and these updates can be done quite quickly, whereas other models would always require complete or more or less complete retraining. And also, as you can see here, our RESCOM approach gave best results. For example, in this hit at 10% numbers here. And we also see that we get meaningful clusterings of the entities, which indicates that the model sort of got some way of understanding what is going on. More interesting is if we get a new user, that's relatively easy to handle. But if we get a new item, we don't have any ratings yet, but we have this meta information, this additional information about the items. So this type of cold start problem can also be done quite well by our RESCOM approach, whereas other approaches have a lot of difficulties doing that. And the nice thing is it's not just a research topic, it also became a reality. So Siemens put this online. So if you order something from this tier selection tool, you get this support which helps you selecting the right items. And currently we are collecting new data, and at some point we will be doing an update of the system. And the nice thing is it went from a research topic to a real application quite rapidly, which made us very happy. So far, I was discussing about this factorization approach. One problem there is that the performance is quite good, but the explainability is a problem. It's not so easy to convey to a customer why this particular recommendation was made. That's why we looked also on path-oriented inference and also explainability approaches. So essentially, a path in a graph is something people can relate more directly to than embeddings, for example. And so here, essentially, we're looking at paths which are supporting effect and paths which are rejecting effect. So it is a sort of an argumentation game. And here are some results. So the query was Richard Feynman, nationality US, and agent 1, which is in favor, says he lives in, found this path, Feynman lives in Queens, and also he found that Queens is located in the US. So that supports this fact. And agent 2, which tries to argue against, Richard Feynman has ethnicity Russian people. So it turns out that his father or his family came from Russia, and Russian people are in the Republic of Tajikistan. So it's not a perfect explanation. The second argumentation might not even be very, very important, but now the user can look at this and say, oh, okay, now I understand why the system predicted that Richard Feynman was not, well, see, the second one was arguing against, so because he argues he's a Russian, so he cannot be US. So I, as a user, can look at this argument and decide, oh, he lives in Queens, so this is probably important, and I believe this inference. Here's another example. Nelson Mandela has profession actor, which is of course not true. The agent who tries to argue in favor says he has a friend, Naomi Campbell, and she stated Leonardo DiCaprio. Okay. But then he has a profession, a lawyer. A lawyer is typically not an actor. And so I have a way as a user to look at the argumentation line and decide if I trust the recommendation made by the system. This whole thing becomes quite complicated. Here's the judge, which makes a decision, learns to make the decision. Agent 1 who tries to argue in favor. Agent 2 tries to argue against. Everything is pretty complex systems with recurrent neural networks, even optimized with reinforcement learning. So in practice, this becomes quite complicated. We're also extending this by also including prior rule-based knowledge. I think this is getting to be an active research area, an increasingly important one. So here it's about drug repurposing. So we know that a drug helps in one disease, and what drug would help in another disease. And this is also sounds like a knowledge graph topic, and we got pretty good results by doing that. And this will also be published here at the ICML workshop. And so we are also trying to not go a little bit away from pure factorization approaches by also analyzing paths, which are sort of instances of rules, and also including rules and maybe also deriving rules. Of course, this is the latter one is quite difficult, as we know from previous experiences. Yeah, so here would be one path. Zorafinib treats liver cancer. Liver cancer resembles kidney cancer, so the hypothesis would be that Zorafinib also treats kidney cancer. So this would be a very simple rule of argument. They're more complex. So this would be an instance of this rule if a compound treats a disease. If the compound treats a disease and the disease resembles this disease. So we're also looking at time dependency in knowledge graphs because there are a lot of important applications in industry like event management, fault management, fault prediction. Because also in industry there are many items who are part of an installation which evolve in time. So there are two ways to do that, at least two obvious ones. One is to just add another dimension to the tensor, then we have a fourth order tensor and we can factorize that. And that's in fact what we're doing in some applications. Another one is to make the representation for an entity time dependent. So this is the second approach, which we're also investigating. And we're combining it with something called the Hawks process, which is a model for temporal processes, which can be permits the fancy modeling or complex modeling of something like LSTM models, and this is essentially the normalization here. Also, this becomes quite involved in practice. It uses LSTMs. This graph Hawks process gives you the cost function, and we applied it to data sets which describe the interactions between countries. There's some databases which are quite extensive and also maintained, so we get new training data every so often. So some application is in healthcare, and I'm engaged in a number of healthcare activities, healthcare related projects. So we first wrote this review article where we tried to analyze what's going on in digitalization in healthcare with some nice co-authors. And then we also went into a concrete project. So one conclusion, of course, is that for precision medicine, so to give very precise recommendations for treatment for a person, you need a lot of dimensions about the patients, a lot of information. Of course, there's also danger because this might lead to information overload. So you have a need for IT support, but you also want to have data from many patients, so you can have a learning healthcare system with different tasks and more in data mining oriented spaces and more in machine learning oriented spaces with prediction and prescription of what to do. So you need to collect a lot of data, and this is what we had done. And so structured data from the EHR, unstructured data from images, genetic information, pathology, we put it all in a collaboration project in a database, and by having our factorization approaches, our modeling approaches, essentially we have a learning database. Two things we are often doing is precision modeling and endpoint prediction. Decision modeling is the idea that you're trying to copy what a doctor is doing, because the doctors have many years of training and education, and maybe imitating them is a good idea. And there's even a benefit, because if you model from many doctors, you get a committee effect, so you might become better than any individual doctor. Now, this committee benefit has been shown in many applications. Another task is endpoint prediction, where so let's look at this one. First, we have background information, which we model as a normal knowledge graph. Then we have sequential information, which we model as a temporal knowledge graph. Then we use an LSTM, a recurrent neural network, for the prediction, and we can predict the decision which will be made, like the medication one should give. But we also can predict the endpoint. Given the medication, how long will the patient live, or what is the progression-free survival time, or maybe even the patient gets healthy. And endpoint prediction is good because you can become smarter than the doctor, because you have information about outcome and can tell the doctor, yeah, what you want to do might be quite nice and also agrees with what other doctors have been doing, but we would predict that with another treatment you might get better results. And in an active in our current work, we are combining these two principles and sort of get benefits from both information sources. So this is now we have data from breast cancer, from Charité, which is nephrology, so kidney transplantation patients. Then eye clinic data from LMU, and we will get more data soon. How do you evaluate such a system, which we are also working on? But one very interesting one is that it's like a virtual tumor board. Tumor board is nice because there all the data come together and at one location, and this is good for training. This is good for a clear decision point, and then later on you get also outcome information. So we did a virtual tumor board where we showed the same data to doctors, and the doctor had to make a treatment recommendation, and one of the doctors sort of was our system, and in most cases, of course, everybody agreed. But when there was disagreement between the doctors and maybe also our system, the doctors preferred typically our recommendation from the one from their colleagues. So this might not be statistically significant yet. We are currently working on this, but it gave us a lot of self-confidence that what we are doing seems to make sense. It's not a completely rotten doctor. Just a hint, yeah. So in ophthalmology, we also did something where we predict outcome different based on different medications people have been using. And in another one is more an image improvement project. So this does not involve knowledge graphs, but by using this great idea of cycle GANs, you don't have to have a clean image and a noisy image of the same kind. You can have a set of noisy images, not a set of clean images, and the cycle GAN approach learns this denoising automatically. Yeah, so missing data is a problem. We have developed a solution. Explainability, we have developed a solution based on this layer-based relevance propagation approach. And as I said, currently we are working on this combination of imitation learning and outcome prediction. Also, just to mention, of course, there's a lot of activities also in our healthcare unit, and they are trying to go up this ladder where they essentially improve what they can show on an image. So, for example, they can find abnormalities or findings. And then on the right side, we have diagnosis and treatment. If you go further to the right side, you have to, at some point, you have to get involved in clinical trials, which is extremely costly. So, the goal is always to avoid that, but to give the doctor as much information as possible to improve the decision making. Knowledge graphs are also great in vision applications, we find, and so I like this proverb from Goethe: "Man sieht nur, was man weiß," or "you only see what you know." And the idea is that sometimes it's called visual relationship detection or scene graph detection. So normal system might say, okay, there's a motorbike on the picture, there's a person on the picture, but we want to extract triple information, like knowledge graph data. So he's a person on a motorcycle. Motorcycle has wheel, person wears helmet, person wears jacket. So this is much richer information. And so we had this idea, but we didn't have data. But fortunately, then this group published something and published also their data. So we then could work with their data. And so the first step is to do a segmentation step where you do this segment subject, predicate, and object. And then maybe you want to predict subject, predicate, object just based on these individual boxes. But that does not really work very well. Also, we didn't find that, and also the other group from 5ILE didn't find that. And the idea is to somehow integrate knowledge about the world. And this is an old idea. Of course, Bayesian approach is based on that. But typically, people don't have a very good level of where they can formulate their prior knowledge. And the knowledge graph is a great way of doing that and very powerful. So, for example, a person in the training data was riding a motorbike. Motorbike had a handlebar, motorbike had wheels, and so on. And a bicycle is very similar. So it's next to can be next to a building, has part a wheel, has part a handlebar. But maybe this link was missing. But by machine learning, we can generalize that a motorbike seems to be very similar to a bicycle in many ways. And if a person can ride a motorbike, it will also probably be able to ride a bicycle. So there's more than just memorization, there's also generalization. And if you integrate that information, and there are different ways of doing that, in the visual pipeline here, the improvement is really significant. And it gave us the ISWC Best Student Paper Award, and then we were also part of the Best Paper Track of ICHCAI. So we used essentially the information in the training data. The group in Stanford used information extracted from text data. But our approach gives better results. Here's some examples. Person next to person, truck on the road, lamp on a box. So this is a mistake, of course. It's a lamp on a bed. And here, motorcycle has wheel. Is basically correct, but it's the wrong wheel. Very important is the evaluation of zero-shot examples about triples which did not occur in the training data. So here, we are the last one here, S. That's our approach. This is visual genome. This is 5ILE's approach. So everybody got that. Bus next to bus. Tree behind bear. We got it. Tree behind bear. Laptop on stove. We were the only one who got that one. And here, bear rides motorcycle. Nobody got it. But of course, it's also wrong. It's a person wearing a bear costume riding a motorbike. So maybe we got that one. We're also continuing this work in the direction of video, in the direction of three-dimensional data, also using transformer networks, which is a recent development in deep learning. So we think this is and of course there are also interesting applications in industry. So if you have a video camera looking at a industrial plant, and the video camera gets deep information about the configuration of the plant, and can match it to past information about similar plants, there are a lot of possible applications there. We're also looking at cognitive aspects, and because we think of that knowledge graph technology might be quite related to some of the memory functions in the human brain. So there are these different memory systems. So this is sort of school book knowledge. There's long-term memory, and there's the one which we can talk about, the explicit one, the semantic memory and the episodic memory. Then also important is sensor memory, which is a quick storage of sensory input. And then short-term memory and working memory, which is really our smartness, where our smartness is. And the important thing is, from our point of view, that we have this visual or perceptual input, and we immediately can talk about it. So there seems to be a link from perception to language. Same is with episodic memory. So this is something you remember. So what happened last Christmas, for example. And we don't just have a fuzzy impression. We can talk about it. We can report about it. Then there's semantic memory about facts we know. Munich is in Bavaria, for example. again, something we can talk about. So there's this transition from sensory information or sub-symbolic information to symbolic information. And so it's not just remembering, it's also decoding. And we have built a decoding approach which essentially produces triples based on information of the latent representations, what we are seeing. So subject, object, predicate, and then the contextual information is the stuff we get from our sensory input. So to make it a little bit easier to understand, this is our architecture. So from the bottom, we have information about bounding boxes on the images, which is then transformed into a representation layer. So this representation layer is quite important. It would cover large parts of the brain and really is a representation of what is being perceived. So you can think of this as a deep neural network. We map it to indices. So we have indices for concepts like entities, things, and so on. And then the brain decides on an entity which it has recognized, and then feeds that back to the representation layer to tell the whole brain, oh, we discovered this is a horse, or this is a cat, or this is a dog. And then, since the decoding, at least we have to decode SPO, maybe we need also longer term memory. We have to feed it to the working memory, which provides some storage capabilities. So there's a natural need for something like a working memory. And also this representation layer sort of can be excited by past memory instances, episodic memory instances, and also semantic memory. And a concept n-gram, so that's sort of the representation of a concept like cat and dog in the brain, would have a pretty localized representation here in the index layer, and then this connection weights here would map it, would then activate a particular pattern in the representation layer. So concept has two representations, one in these weights here and one in the indices. This concept of the representation layer sort of reminds one on the Haynes approach to the global workspace or blackboard theory, that the brain, when it's decoding something, is really a serial process, but because it's serial, we need some storage. Of course, this is ongoing discussion, but our model would not violate or rather support this idea. So in a way, it's a neural network type of implementation of the perceptual model I've shown you before. You can also uncode it in time, and then you see how the different information from the bounding boxes come in, how they activate the representation layer, and then the index, and then the index backwards activates the representation layer again. And here's the hidden layer, the memory layer, which stores the past decodings. This is how we would speculate how it is represented in the human brain. So the visual information comes to the primary visual cortex. The representation layer is sort of distributed in the brain. So do I have this on the picture? No. So for example, if you think of hammering, then you would activate the sound of hammering. So this would all go in here. No? The typical look of a hammer and also the movement of hammering. And this is sort of, there's a lot of evidence which shows that this is what's going on if you think about hammering. Here would be the index layer and the temporal cortex, and then here would be the feedback between the two, and then the working memory is typically assumed to be more in the prefrontal cortex. So our approach, which is the first three ones here, shows pretty good results if we compare it with similar approaches which are not oriented on in terms of biological plausibility, but we also didn't try to optimize our model for best possible performance. we wanted to show that it gives performance which is comparable to other approaches. And then the question is this really going on or something like this in the brain? And there's some support for it. So this is a very famous paper from Quiroga and co-workers, which analyzed part of the temporal cortex. So these are people which have operations, and then they first check where the language regions are, so they are not heard. And during that time, that you can poke around a little bit in the brain. And they found this one neuron, for example, which is exclusively answering if somebody looks at or thinks about or hears about Jennifer Aniston. Sometimes they're called Jennifer Aniston neurons. And they're quiet, a single node is quiet for anything else. And they found a number of them, Halle Berry and some others. So this also the authors don't argue that there's a single neuron representing one person, but maybe a small set of interconnected neurons which are responsible for for representing persons. Of course, this is debated. Nobody in brain science agrees on anything. They agree on a lot of things, but there's always disagreement. So it's not that everybody thinks this is the truth, but it's a good indication that there's some form of local representations of concepts in the brain. And also we can map, so this is when people hear about stories, and then people try to map the concepts people are hearing about to brain regions, and you see that they found them everywhere on the brain surface. It's also a Nature paper by Hood and Galland and other authors, and so this would be what I would consider the representation layer. For example, the word top has two representations, to argue that this is semantic representation and not a word representation. So so one is on top of something, and one has the meaning of a bikini top. So that was their example to show that this is a semantic map and not just a word map. Finally, we're also looking at quantum computing, because there are some scalability problems with knowledge graphs and knowledge graphs learning. And I'm working here with a very good student, Yun-Pu Ma, who's also from physics. So he mostly developed 3 different algorithms. One he called quantum circuit embedding model, QCE, one fully parameterized quantum circuit embedding model. So this is a variant of the first one. And then quantum tensor SVD models. So you get these type of circuits to implement the algorithm. So the challenge here is to find a version of a factorization approach which can be mapped on the circuitry which is available in quantum computing. So for example, these guys here, these G's are variational gates, and these H's are Hadamard gates. So you cannot just say, here's something, please do it. You have to map it to this type of architecture. Of course, this is far in the future. The hardware is not yet there for doing that, but we want to cover this knowledge graph space, and also want to explore this direction of research. And we're also involved in a funding project, which hopefully will be funded. By mapping the factorization approaches to quantum, we get quantum improvements or quantum speedups. This is the most important one, because NE is a number of entities. So we have something from linear to square root, but this would be really interesting because it's even a better scalability possibility. But again, these are not things we can even experiment with on a true quantum computer. This is then verified on different simulations, which permit the simulation of different number of qubits in sometimes quite big supercomputers. So I should come to a conclusion. I think there's a lot of potential in the combination of knowledge graphs with machine learning and deep learning. So it's not just knowledge graphs. Knowledge graph is great, but I think the full power comes about when you combine it with machine learning and deep learning. I've shown a few examples and research results which potentially substantial impact at Siemens business. So yeah, the whole knowledge graph activity at Siemens is quite large. We have a whole team led by Steffen Lamperter of maybe 30 people who are doing all sorts of knowledge graph oriented projects with the business units. We have also another group of the same size who's doing more machine learning and NLP techniques. My team is more on the research side. I have people at Siemens and also people at the university I work with. So that's a really nice research team. Yeah, we are also embedded in a number of networks. So here's MCML, that's MLWin, which is a project I'm heading. So I'm the consortium head here, exploring different combinations with knowledge graphs and machine learning. I'm also involved in Alice in different activities. So there will be a Munich node of Alice where I'm a faculty, and I'm also suggesting a program for semantic, symbolic, and interpretive machine learning, which partially is also knowledge graph oriented. So I'm fascinated because I think deep learning, machine learning, and knowledge graphs are really the things we need in many applications. I see a real long-term perspective in the different fields, but also the combination of the different fields. And yeah, I hope you enjoyed my presentation. And I think now we're turning to the live version of this, and we are coming to the discussion. Thank you very much for your attention.